So in this course we will be mainly focused on what is called as the digital part of the VLSI design, okay, or we can call it as digital VLSI design. The other part is analog VLSI design is there, but we will not even touch on it. And there is also a combination of the two, okay, you have both together, and that is called mixed signal design. So you have the digital part as well as the analog part together in one chip. Some of your mobile phone chips are like that. So we will be focusing mainly upon this digital part. Now most of the chips which are manufactured, they are digital. Maybe 80% or more chips are digital chips, okay, and the design of these chips are completely automated, and it is all done by software. So there are various steps in the design. Each of these steps are done with the software. So I hope you know what is the full form of VLSI. VLSI stands for V for what?
Very large processor.
Yeah, very. L for large. S for scale. I for integration. Not the integration in calculus. Here integration means putting many circuit elements together in one chip, integrating together, putting together. So that is the, and very large scale is referring to the level of miniaturization, how small these components are. So we are putting things together in a compressed way, and for that we need to have every component or devices like transistor mainly should be very small. Okay, so how small it is, that depends upon the technology node, but VLSI is a very common name which is generally applied for any chip which has say more than 10,000 transistors inside it. Okay, so that is what we mean by very large scale integration. But right now it is nothing like 10,000. It is going to be in the range of tens of billions. 1 billion is 10 raised to 9, so 10 billion, 30 billion. So that is the number of transistors in one chip. For example, if you look at any of the processor chips, so there are, that's a digital chip. All the processor chips are digital chips, and there are, each chip will of a processor will have billion or near to billion. Earlier chips may be millions of transistors, but these days it has come into the number of billions of transistors. So that is the kind of number that we are right now dealing with, and it is never possible to schematically wire up the circuit which makes these processors one by one. It is impossible. Even you can't even sit and count these transistors. It is that many. So we need to automate this so that all design will be done with the help of softwares. So that is why in digital VLSI design we mainly deal with the softwares. So the first step in the design is what we will begin with. First step is basically coming up with the specification. Okay, you need to specify what is the functionality of the the chip that you want to design. Okay, and there are various types of chip which I will come into later, but the very first thing, if even before doing anything else, we need to come up with what is to be the functionality of the chip that we want to have. So initially it will be put in words, but then from words we need to go into more consolidated architecture or block diagram level specification. Okay, so we need to specify, we need to have a chip with this much amount of memory, and it should be this kind of memory, it should have an ALU block, just like you see the architecture of a processor. So depending upon what is the kind of circuit that you are wanting to design, you can come up with a architecture of it, the global architecture of whatever is contained in that. So there will be various blocks, each block will have different functionalities, etc. So first is specification, and then from specification you will have to come up with a block diagram. Now when you want the software to understand your architecture or your block diagram, you need to describe it by using some programming language. So the language that we make use for describing a digital hardware is what is called as HDL. Okay. HDL stands for hardware description language. Okay, hardware description language or HDL. There are various language. Most popular one are Verilog, and the other is VHDL. Okay, so there is a history of all these languages which I am not going into. The basic difference, if you look from the historic point of view, Verilog was mainly to give a more detailed description of the lower level part of the description, that is the transistor level or gate level. So lower level is basically transistor and the gate, and higher level is basically like your architectural level, like memory, ALU, that sort of level. So these were like historically it evolved like that, but right now there is not much of a difference. You can do pretty all the things that you do with one with the other also. So it is either one of it, if you know, that is good enough. Okay, so we will focus on Verilog. So today is a lab session, as I told. So we will look at how we can describe digital hardware. So what is HDL used for? To describe, as the name signifies, to describe a digital hardware to a computer system. Okay, to describe a digital hardware to a computer system, because then rest of the job is going to be, once you describe and give it to the computer properly, then the job will be done by using the computer. Okay, and this is not the way usually we do it for analog circuits, because generally analog circuits are smaller circuit, maybe 1,000 transistor or something like that, maybe commonly, or lesser than maybe 100 transistors or 100 to 1,000 transistors. And so analog circuits are usually smaller, but since they are smaller, it consists of smaller number of transistors. You can even put in those transistor and make a schematic design. So that is possible with analog circuit because the complexity of the circuit is less. Okay, of course the analysis part may be tougher, but the complexity of circuit is complexity in terms of the number of elements present in the circuit may be lesser for an analog circuit. So we still use schematic editors to draw the circuit and specify your circuit for an analog domain. But for digital domain, as I told you, you are dealing with billions of transistors. It is impossible to schematically wire up the circuit. So we need to use Verilog or VSTL. These are not the only hardware description language. There are many more. Okay, something called System C, etc. So we will not go into all of that. We will stick with Verilog. You should know at least one of these language, and you should know it very well as much as possible. There is a lot of job opportunity if you are a master of any of this language. Lot of job opportunities. You can so take this lab very seriously, and especially the Verilog part of it. Lot of jobs are available. Those who can write code to describe the design that you want to do into the computer, and do it rightly, and then simulate it and see whether what you have described is correct or not. Okay, and then comes the next level. Once you pass the description and the verification of that description, after you successfully do that, then we will go to the next step. Now I am not going to tell you what is the next step. That I will come into at a later time. Okay, so Verilog is one of the language which we use for describing digital circuits. Okay, so to see or to practice the Verilog coding, we can make use of a open source platform which is called Icaris Verilog. So I hope you have already done the installation. So if in case you have not done, what I am going to show you now is for Windows systems. So all you need to do is just type Icaris Verilog for Windows. Okay, so you just type this, and you see the first website that it goes into. You will get this website where you can download this open source version of the Verilog coding platform, which is called Icaris Verilog. So depending upon your system, whether it is 64-bit or 32-bit, you can choose cross 64 or cross 86. I have installed it, so I will not be downloading it again. So once you click on any of this, it will be downloaded, and then you run it just like you would do any exe file. And in the process of running, while installing the software, it may also ask you for, do you want to install GTKWave, so which is also included in for example, if you download the first link, it is already included in that download. So you tick that because we would require that also, and install both. And once your installation is complete, then you can just okay, so you will get an icon. You can have a what do you call it, shortcut on your desktop also, or in the start button you will get this Icaris Verilog. If you click on that, it will take you to the folder in which this program is installed. Okay, so it is called not Icaris Verilog, it is called iVerilog. So that folder will contain various subfolders like bin, GTKWave, etc. So if you want to run the code, what you need to do is basically go into bin and write your Verilog programs here. Okay. Now if you want to keep all your program in a separate folder, in a separate drive, then you need to do certain certain additional thing. So I will tell you what additional thing you need to do. So for that you just go to advanced system setting. You just type here advanced system setting. So you will have this advanced system setting. So you go there, and if you go here, you can see there is a tab called environment variable, and in that environmental variable you will have something called path. And if you click on the path, so here there are some specifications, and you need to add these two paths here. Okay, one for Verilog and the other for GTKWave. So this will help you to run your program, store your program in a different drive, in a different folder, wherever you want. And since this path is there specified here in the environment as an environmental variable, then whenever you run an Verilog program or a GTKWave program, then it will automatically go to the appropriate folder and run it. Okay, so you don't need to know about it. All you need to know is like where you are standing. So to that folder you need to change your path, because we are going to run the program from the command prompt. So in order to add these two, if it is not there in your system, you just click on here new, and when you click new here, you can just copy the path and paste it. So to copy it, you just go to the folder and click here. It will show you the path. Copy this and go here, and in the new you paste it and then click OK. Similarly, you can go to Verilog, inside that GTKWave, and then again bin. You copy this path also, copy this, and then go into the environmental variable and add a new. So these two paths, the last two lines, if you can see, so that will help you to run this program from anywhere in your computer, from any drive, any folder. Okay, provided you get into that folder and run it. Okay, and that is much more convenient. Since I have done it, that is how I am going to do it. Otherwise, you need to write your program or code in the Verilog and then /bin. So that bin folder you need to put your program and run your program. Okay, otherwise it will not take. Okay, so that is one additional thing you can do if you have not done. Alright, so my program I have I think stored in this VLSI design. Yeah, so here is a folder. So I have stored my program here. I just wrote one program here. So I am just copying this, Control C, and then I'm going to open my command prompt, CMD. So command prompt will open. So this is my command prompt. You just type CMD in your run or Cortana, wherever, whichever version you have of Windows you have. So this will open up, and then what you do is you need to go to the folder. So you type D colon. If you type, it will go to the D drive. Now I want to change my drive to the folder where I have stored the program. So this is the first thing you need to do. Control V. Okay, I have copied it earlier. So in D I have a folder called online class, new VLSI design, then Verilog programs. Okay, so CD, change the directory. So this is my directory. Now once you enter, now you are free to run your code. Okay, so in order to see what are the contents in the directory, this is like DOS operating system. So dir, if you type, you will see what are the various files or folders inside this the folder in which we are standing. So Verilog underscore program, so that folder contains a few files. So 2-3 files are there. The names are listed here. When it was created, all the details were there. Okay, so I just created it yesterday. Okay, so before we proceed, I would like you to see what I have written. So here, if I open, there is a .v file. So how to create this .v file? You can open any text document. Okay, if you right click, you can type new, and then you can type this text document. Okay, so if you like that, you open a text document, and then if you can install this Notepad++, it has some added advantage, and the advantage is that it can sense the the keywords and show it in a different color. If you are writing a program in a normal text document, which we call as Notepad, then it will all be in black fonts, and color code won't be there. So if you want to see it with keyword in a distinguished way, then use Notepad++. You can just download, just like you search in the net and go to the appropriate site and download it. It won't take much time. Okay. So if you open it in a Notepad++, it will be opened like this. Okay, you can see that some keywords are highlighted with different colors. Okay, so that way you can understand what kind of this is a command, or this is a standard keyword, or etc. Okay, now I am going to explain you this particular code which I have written here. Certain things you need to learn. Okay, in the sense by doing it you can learn it. So it is better I explain it line by line, everything that is here. It is a very small circuit, and let me draw what circuit I am going to describe. Okay, so though I said usually billions of transistors are there in a digital design, but right now we will not take up anything like that. We will use very small digital blocks which we have studied in your digital electronics. So I will just repeat some theoretical aspect of this block. It's basically a 1-bit comparator. So I hope everybody remember the operation of a 1-bit comparator. So 1-bit comparator. Now a 1-bit comparator, if I draw it in the form of a block, then I can tell you the functionality. Okay, the functionality is that it will take two single bit numbers, say A and B, and this is my 1-bit comparator, and it has 3 outputs, and only one of them will be high at a time, and that depends upon what is the value of A and B bits. So one is called greater than, or the other is equal, and the third one is less than. So greater than means A is greater than B. Okay, so it means this, A greater than B. So single bit, for example, if A is 1 and B is 0, then A is greater than B. So G output will be high and the other two will be 0. Here it means A equal to B. That means either 0 0 or 1 1. E will be high and the other two will be 0. And similarly, less than means A less than B. So when is A less than B, A is 0 and B is 1. Okay, so there are only 2 bit. One is A and one is B. So if I write the truth table, it's a very simple, and there are 3 output, G, E L. Okay, you can take it in any order. I'm just taking a random order, 0 0 0 1, and then what else, 1 0, then 1 1. Right, so this is the 4 combinations of inputs that you can have for 2 single bits. Individually they can be either 0 or 1. Now in the first case, you know that it is equal, so G is equal to 0, E equal to 1, and L is equal to 0. Next case, A is 0 and B is 1. A is definitely less than, so here it is going to be 1 and 0 0. Next is 1 0, so it's A greater than B, so these are 0. The last one is 0 1 0. Okay, so as I told you, if you see, out of the 3 outputs, only one of them is high at its time. Okay, now how to design it? Very easy. If you look at any one of the output, let's say G. So G is basically a function of A and B. It is basically what? It is basically 1 only at one case, that is when A B bar. That's the expression, Boolean expression for it. In SOP form, you can write it as A B bar, right? A is 1 and B is 0, so B bar is 1, so A B bar. And similarly, you can write, okay, let me write L next. L is what? L is also one for one combination, and that is A bar. Okay, so now what about E? So E is also a function of A and B. If you want, you can do it with the K map and all. Okay, so that is one way you can proceed. But otherwise, if this is not the case, nor if neither G or L are 1, then we can say the remaining case is basically E. Okay, there are 2 such cases, 0 0 and 1 1. So if I basically take a OR of this, okay, A B bar plus A bar B. So this is a case where G is 1 and this is a case where L is 1. So adding them together will take both of the case where either of this is 1. Okay, this is basically XOR gate operation. Now in this, if this is 1, I want it to, E should be 0, and all the remaining cases which are not included here, I should have it 1. So what I need to do, I need to basically do a NOT operation of that. So you can write it as basically G plus L the whole bar. Okay, so that's basically a NOR gate you can use. If you have G and L, I can use a NOR gate to construct E. So this is the design. Now you can draw the circuit. If you draw this circuit, so you have A and you have B. To get G, what you need to do? To get G, what you need to do is basically take A and then take B and complement it, and then take an AND operation. So that is your G. Similarly, how to get L? L is obtained by take B directly and then AND it with the NOT of A. Okay, A bar, then AND B. Okay, this is AND operation. So that will give you L. Then G plus L, you pass it through a NOR gate that will give you E. So you extend. So this is your G output, E output, and L output. So this is the design. Now we want to describe this design into the computer. We need to describe this hardware into the computer. Okay, the functionality of the hardware we need to specify by using the Verilog language. So I will go to this file. That specification is done here. Whatever I have told you so far is specified here. I created a block. Okay, I created a block just like here. This block diagram, this one bit comparator block is there. It has 2 input and 3 output. So that is the first thing that I will specify. So the keyword is module. Module is like specifying the function. Whenever you say a particular block, so that block we will call it as a module. So that module has some inputs and output. So the inputs are x and y. So I can give this like x comma y. So these are the input. Then I can do it multiple different ways. This is one of the way. Okay, so you can specify it as here like this, or that is x input x comma input y. It's not necessary that you have to have different line also. You can do this also. There are lots of flexibility here. Okay, input y, input x, x is an input. That's what it means. So comparator is the name of a block, and that block has 2 inputs x and y. They are single bit, and then it has 3 output. That is G, L and E. Okay, greater than, less than, and E for equal. Now I can also remove this and write like this also. This is also okay. It will take it as x and y are input. Output is G, L and E. Okay. Okay. An alternate way is also there. You first don't say whether it is input or output. You will just write like this. Okay, x comma y comma. These are the ports, port terminal, and then separately you say input x comma y. So this way you specify input, then output G comma L comma E. This is also possible. Okay, so it is up to you, whichever is the way convenient for you. You write whatever way. So I showed you multiple ways. And I have defined a block with ports x, y, g, l, e, and then I say the port x and y are input and g, l and e are output. Now comes the description of the internal details. Okay, how the output depends on the input we need to specify, and that also you can specify multiple number of ways. Okay, and one of the most easier way of describing it is basically to say that G, that is the output, is basically x, and it's something like writing Boolean expression, not of y. Okay, this tilde here is basically inversion, say unitary operation, unary operation. Like binary operation, and is a binary operation. You have two variable x and y bar. Okay, you are taking two variable and you are doing a AND operation, whereas not is basically a unary operation, which means you have only one variable. You take the NOT of that. So first you do that, and then the preference is like is for unary operation, preference is more than the binary operation. So it will automatically first take y bar, and then the result is ANDed with x, and that is assigned to G. So this is like you write the Boolean expression which we saw earlier. So these expressions here, you write using the syntax of Verilog. So for and you use ampersand, for not you use this tilde, and for or you use this. So this is or, you just a vertical line is or, and then you take the or operation, you have to put a bracket, otherwise the result will be wrong, because if you don't put the bracket here, the G bar will be ORed with L. So it is very important you put a bracket so that the OR operation will be taken first, just like board mass you have studied in school. Similarly, there is some preference. So if you want to take OR operation first, you put the bracket there, and so that's it, and you end the block with the keyword end module that doesn't have any semicolon at the end, but all other statement has a semicolon at the end. Okay, so this is all what it takes to describe our hardware, which I have drawn earlier while discussing. Now once we specify the hardware, we need to test it. So when you want to test it, you need to how do you test it? If you have a block like this, so this is suppose this is the block that we have. Okay, so this is all in a block. I have a block here. So this is a block, and then the name of the block is comparator. That's what I have specified. And I said A, B, there are inputs and outputs. Okay, so I think I set up this. Okay, let it be like this. So okay, so this is one block, one port, and 3 input port and 4 output. So now I want to test whether. So what I need to do. One way, if this hardware is before us, then what we need is we need a power supply, right? For testing it, we need a power supply which can give you say supply 0 and supply 1. Okay, so logic 1 and logic 0, and I have to basically test the truth table. So what I will do is I take wires, and then I will connect here another wire. If I want to test for 1 1, then I'll take another wire and connect here. So I connect 1 and 1 at A and B and see so what is the output. So in order to see the output, what I require, I need some LED kind of thing. So I need some kind of bulb to see whether it will glow or not. So that will be grounded like this. Another LED and the third LED. So this is how you will test. So you give whatever combination you want. So if you want to test for 1 1, I would expect that this will glow and the other two will not glow, and therefore 0 0 option is correct. And then what I will do, I will disconnect this and again take this wire and connect to supply 0, and this time again I will check what will happen. So A is connected to 1 and B is connected to 0. So A is greater than B, so I should get this glowing and the other two not glowing. So my point is that in order to test a physical hardware, this is what we do. We need some power source, and then which will give you, from where you can connect wires to the inputs, and then the output we will check by using some kind of LED or some bulb or something like that, or you can do it with CRO also, or a voltmeter also, multimeter also. So you have to use some additional external thing, and in Verilog what we do is we design what is called as a test bench. The test bench is something like this. Okay, this is a test bench, and inside this test bench all the except this so this is my test bench where I have all this other things which are needed to give input and take output and display. All these are there, and what I will do is that maybe I don't require this. Okay, so inside the test bench I will make a copy of the original block, which is I will make a copy of this block. So that process is called instantiation. Okay, instantiation. So instantiation means you are basically creating a copy of the hardware that you want to test. Okay, so this is the block under test. Okay, BUT, or device under test, DUT, or unit under test. You can give any name, UUT, BUT, or DUT, or any name which you like. So we are instantiating one block of comparator, and then we have set up some source to give input and some output. So this is also a Verilog entity, okay, or module. Okay, so this is the test bench module. So we will have to write a test bench module, and inside the test bench module we need to instantiate the design module that we want to test. Okay, so this will also be a so this will be the global program, or the overall program will be a test bench, and that test bench will contain a module which we have created, which is the device or the block that we are testing. Okay, and then some additional thing. So now let's go back. So initially what I said is that this is the block description. Now in order to test it, we need to have some other you can name whatever you want. The test bench module, you can here it is named as stimulus, but if you want you can give a different name like test bench or something like that. So this is the test bench TB, and inside this test bench, if you see this line here is where I have created a copy of the block which I have described earlier. So basically you are calling a function, just like in C program you call a function, but there's a difference here. Here when you call a function or a module, you are basically creating a hardware. It is equivalent to creating a hardware, putting a hardware inside, a block inside. So that is what I earlier specified. This block here, comparator block, is now created with that statement. And once you create it, now we need to connect some inputs and outputs, right? So now what is the input that I want to give? So let's say that I want to give, say, A is my wire from the power supply, and B is so A and B are basically the power supplies from which to which we are connecting. Okay, so basically if you look at here, so this is A, and so here it is called X and Y. Okay, so the port we have defined it as X and Y, and this is what was G, E and L. So this is how we have defined in the design block. X, Y input, G, E, L small as the output. Now what is A? A is basically the signal, which is either high or low, that we have to specify, but we need to connect this wire which is from the power supply to the input of the block. So that is also given here. So comparator unit, now so this let me see, So I have now given a different name. It is better to give same name, so that now I am not very sure whether I should put A here or A inside. So let us check. So this is B, and then let me give here G L E. Okay, so for making things simple, you can give same name. So this will be G L E. So in the design module, I have given this capital letter GLE. What did I say earlier? No, there we have given small letter. So let's stick to small letter here. G L E. Okay, and so this is G. And this is basically a mapping between the external wire through which we give, and here I want to say that it is G L E. Now you see that here one is defined as reg. Reg means register. I can give it like this also. So two of them which are input. So input is taken from two registers basically. Okay, so here I have said power supply, but these are basically output of two registers A and B, because later we need to change this variable, we need to reset this variable. So we will make single connection, a connection like this, and then so this is my A and B. So A and B will automatically change through program. So you can output 0 0 or 0 1 1 0 here. Okay, so this will be a flip-flop kind of thing which can store value. It's a register, and then depending upon what we want to give there, so we don't need to fix it to 0 or 1, we can give anything by program. Okay, so we just need to connect it. Okay, but by programming I can change A and B, so this will become a register. Okay, so that is more appropriate to say here. So register content we are able to change, and then the output is basically taken as a wire. Okay, because you can read what is connected to the output. You should not put a register there, you should put a wire. So whenever you write a test bench, whatever is the input to the block should be connected to register, or in other words, the inputs are driven by registers and the output could be a wire, or it could be a register also, but you can keep it as wire. But you should not keep wire here, because wire you cannot change the value. Okay, in order to change the value of the that block register, you should be able to program that part, and it is only possible with a register. So this is very important, this line. We need to make it register, and from register you need to connect it to the inputs. So that mapping is what is shown here, and then whatever is the output. So if I go by the same way, so the output should be connected to the block. From the block should be connected to the test bench. The capital G, L and E are basically the wires which are going to the light, okay, for displaying the output. Okay, so that could be a wire, so it is defined as wire. So we have mapped it. Okay, and then what we say is that we are basically starting a block, so which ends here. It's called the initial block. Now initial block means for initialization of that means what are we going to give what are the signals that we are going to give. So what we are going to say is that at time t equal to 0, initially time t will be 0, the starting simulation is at time t equal to 0, we give x equal to 0, y equal to, so here now I should say a equal to 0 and b equal to 0. So I told you we can program it. So this is how we program it. Initially we give a equal to 0, b equal to 0. From the register output we will give a equal to 0, b equal to 0, and then we wait for 20 units of time, and is it a millisecond, nanosecond, that we need to specify in the very first line. Here there is a command called, this is a special command related with time. It says it is whatever unit you write here 20, it will be interpreted as 20 nanosecond. So for 20 nanosecond it will wait. That means whatever input we gave earlier that is a equal to 0, b equal to 0 will remain for 20 nanosecond. So the unit is interpreted from here, and picosecond or you can give this is the second parameter is the resolution, so you can give 100 picosecond, okay, or 0.1 nanosecond. So that will be the resolution in the plot, okay. So the unit which we are mentioning here, that is the unit of this number. So that is the first one, bar the resolution, how how much detail you want to see the waveform. That means if you expand the waveform, you can go up to 100 picosecond detail. That's what it means. And there is a comma here, which is basically you can find that just at the same what do you call it, the tab where on the screen on the keyboard just beside the one, so you can use that to create that particular comma. So it has some name, I forgot what exactly is the name. If anybody remembers, you can tell me where you find the tilde in the keyboard. On the same keyboard, the same key which has tilde on it, if you shift and press it, you will get this comma. So that you have to put. Then time scale 1 nanosecond, which is a unit, and then 100 picosecond, that is your the resolution in the plot. Okay, so we define the test bench. We are now discussing the test bench. We instantiated one block, and then we mapped the test bench variables with the block variables, that is establishing the connection. Then we started giving the input, then we wait for 20 nanosecond and change y. Y is changed means it will go to a equal to 0, a is not changed, b is changed to 1. Then a is 1 and b is 0, and again wait for 20 units of time. Here it is 20 nanosecond, so in the plot it will be shown as 20 nanosecond, and then you have b also going to 1. Okay, so then you wait again for 20 nanosecond and you finish. So this sequence in which the values of the register is going to change, this is the reason why we need to keep a and b as register, and we need to put them in this initial block. Okay, so and then vary according to, you can vary in some other fashion also. It's not necessary that you vary only this way. You can vary in some random fashion also. It is not necessary that you vary 0 0 0 1 1 0 1 1. So that's how we have varied, but you could vary in some other order also. So this is the test patterns from the register. They are put in initial and then begin and end. Between begin and end, if there are multiple statements, if there is only one statement, begin and end is not necessary. Just write that statement under the keyword initial. Okay, and that will be starting from t equals 0. Initial means you are setting the time to 0. What you need to do, there is a second initial block. It is not necessary that you need to have a second block. You can put it in the first block also, but then you have to put all this command basically at the beginning, otherwise it will mess with this part of the code. So it is better to put it in a separate file. And what does it do? Basically it is creating a file. So whenever there is a change in the values of any of this A, B, etc., or the output G, L, E, then that value change will be dumped into this file. Okay, so value change dump. Okay, that is VCD. So whenever there is a change in value and what time it is going to change, all this detail will be dumped into a file. And what you need to dump is basically you have to give the module name, everything in the module TB if you want to dump. So whatever is in the module, variables are A, B, capital G, capital L, capital E. These parameters will only be dumped if you give 1 here. If you give 0 here, then it will also take X, Y, G, L, small g, small l, small e, also it will dump. Okay, so it's up to you whether you want only the port terminal of the test bench or the instantiated block also you want to dump those variables also. Accordingly you put 0 or 1. I am putting 1. I only want the test bench data only. I want to, if there are multiple say blocks, then you can give by comma also. Then the last one is, what are the variable you want to print on the screen. Okay, first is T for time. So I am saying there is a command called $time, which will basically whenever there is a variable change, it will detect what is the time there, and that time will be printed as in a variable called T. And then now it should be A. So I am going to print A, then B, then capital G, capital L, capital E. Okay, so I have to now write A. Okay, so here I have to write B, G, L. So these are basically labels. So labels I can give X and Y also here, so that's okay. I can give X is equal to, because X is basically connected to, and here it is Y. Okay, let's keep G, L like that. Okay, but here these are variables and these are labels. Okay, so you write some strings, you can give first input also here, second input is equal to, but these are the variable, whatever whatever is the value of A and B will be assigned to that label. Okay, so T is a label for time, so this is a inbuilt command, and similarly whatever is started with the dollar, that is, these are some system command which will basically do certain operations. It's different from these keywords in Verilog. Okay, so these are basically to do some specific task, whereas these are for programming. We use these keyword, this. So the blue and violet have slightly different meaning. Okay, but they are all special words which are understood by the compiler. Okay, then we are ending the test bench here. Okay, so we save this, but we have made some change, so we are saving it. Now I have a doubt whether AX this order is correct or not, so I'm going to just make a try and see whether this is the right order. If not, we will have to reverse it. I have to put X outside and A inside. Okay, so that is something that I'm not very sure about. So we go to the command prompt, and the command is basically Verilog. Since I have added the environmental variable that I have added, I can run it from this folder without problem, otherwise it will not. Now whenever I run this, I need to I will get an output, So if I want to name the value of the output file after compiling, so I can give -0, then the file name. The file name which I have, the .v extension is comparator.v. Okay, so here -o, after that I can give a name which I like. Okay, so let me give a comp underscore out. Okay, so this is just, okay, let me, okay, comp underscore o, that's basically the name of the output file which I will get. So this is my input file, comparator.v, which is same as here. You can see here the text document, or this Verilog file, program file, is where the code is put, that has comparator.v, and then output will be dumped into this particular compiled output will be dumped. Verilog is the okay, so comp underscore. Okay, now let me run. If there is any error, it will show up. So you see that the order in which I have given is not the right, is not a part of UUT. A, B, G, L, E is not a part of GUT. So that's what I said. I am not very sure whether it is in this. So this should be X and this should be A. So whatever is the test bench thing should be inside bracket. The other module thing should be outside. So now everything I need to change. So this is how we learn. L and then capital L should be inside. So mapping has a syntax, so we need to follow that syntax. Okay, so again I am saving it. I can use arrow keys to come back to the same command. Now it has run without any problem. It has run. Now to see the result of the value, we use VVP. This is the output file, comp underscore 0. So you see that it is printed at time t equal to 0. We gave 0 0 as the input, and G was 0, L was 0, E is 1. Yes, that's what we wanted. So our description was good for at least that combination of the input. Then we waited for 20 nanosecond, and then another input combination, x equal to 0, y equal to 1 is given, and we get G equal to 0, L equal to 1. So that means x is less than y. Yes, that's correct. It cannot be equal, it cannot be greater. Similarly, 1 0, G is 1 and it cannot be lesser or equal. And finally, t equal to 60, we have 1 1 combination given, and then we have equality. Okay, so our simulation is done, and the result is printed out by using VVP command. The compiled output is run with VVP command, and it will show whatever quantities that we have said we should display. So the monitor command here, it's a command here. All of this dollar thing is a command. So it will perform certain execute. It will execute. It's a command to the compiler basically to do some things. Okay. So we said print this A, B, G, L, E, and it has printed it. And for each combination, it has printed it with the time tag. So we have to insert the time tag explicitly. Then only the time will be shown. Otherwise, without time only it will show. Okay, so success. Now we have also done a comparator comp underscore w.vzd file. So let us run that file. So for that you need to install GTKWave. I told you it will come along with your Verilog installation. So If you are doing it in Linux, I think you need to do that separately, or Ubuntu. Gradually I will move to Ubuntu. So today I have just started with Windows, but we may have to move to Ubuntu because the Windows whatever we can do next is limited. So but to start with, let us maybe for a few classes we will stick with Windows, and then parallelly I would ask you to partition your memory and then create Ubuntu in dual mode, and then install. Installation is very easy. You just need to run a command. You can just I have attached a file in your Google Classroom. You can follow those. Okay, so the next thing I want to do is basically I want to see the waveform. So same information, but I'm going to plot it as a waveform. So for that what we need to do is GTKWave, just like Verilog. Now we say GTKWave, and then whatever is the name that I have given for the VCD file, so comp_w.vcd. so a window will open now. Okay, no variables are shown here, but if you click here, I have the test bench, all the variables on the test bench here. So if you click here, it will come. Okay, so if you double click on each of these variables, say for example register A, register B, from where we gave the output, and then finally our LEDs are E, G, L. Now it is showing 1 picosecond. See, because the resolution was 1 picosecond. I hope I changed it. It came 1 picosecond. Should be 100 picosecond. I've given 100 picosecond. Okay, so let's just, okay, what you need to do is you can fit the whole waveform, because our change of input happens when it happens at like 20 nanosecond. So if you see it in a 1 picosecond resolution, you need to shift this tab so much. Okay, and that's very inconvenient. Okay, it's changing, you can see that, but this much resolution we don't require actually. So what we do is we fit inside the window the whole waveform. So click here, so that will bring to the proper scale. So you can see that this is 10 nanosecond, 20 nanosecond. From up to 20 nanosecond my A and B were 0, the register output was 0, and then I made B1 and A was 0, and then A1 and B was 0, then both 1. So 0 0 0 1 1 0 1 1, and then I have my equal symbol is high for 0 0 combination and 1 1 combination. Everybody can see that. And my greater than is only 1 when A is 1 and B is 0. My less than output is 1 only when A is 0 and B is 1. So that's it. So we can see the waveform. So this is a better way of looking at things. Okay, so I want to see why the resolution became 1 picosecond. So what I would do is I would rerun it again after deleting this. Yesterday I might have. So actually I need only one file to start with. I have opened that file. Okay, I have made some changes, saved it. Now I go to the window. I'm going to repeat whatever command I gave. Okay, so now one more file will be created. My compiled output is this com_o. That's the output of comparator. Now I can see VVP. Okay, that command is also here. Run that. I get these output. Okay, now I got the VCD file also dumped there. When I run the compiled output, now I do GTKWave comp_w.vcd. Okay. Okay, I think maybe by default it is like this. It's the same thing. Okay. So I fit into the screen. Okay. Alright, so there is no difference. Okay, there are some scale. If I see the full waveform, I can see some scale here. 10 nanosecond, 20 nanosecond, which is divided into see. So all these values where the cursor I am putting is here. So if I put here this 1 0 0, okay, A B I have not put. Okay, so for 0 0 output is 1 0 0, so you can see that. And here A 0 1 I have L1 and E and G0. So you can just click here, the cursor will come and the values corresponding to the cursor will be shown here. Alright, so now it's already 4 o'clock. Now let me know if you have any doubts. Are you there or?
Sir, explain the line 15. Line number 30.
Line number 15.
30, 30, 30.
30. This one. This is.
No, sir. Actually, move downward. Move down. 38, sir. 38.
38. Oh, right. So 38. As I said, there is some portion. It's basically a command to the compiler that when you run the code, you need to monitor these values. Monitor means something like print command in C. So when you do the printing, you can print some string also. In Python also you can do like that. You can output you can write in words and equal to, then you put the variable there, and so it will print as output equal to whatever is the value of the variable. Similarly, t equal to we write, and then the variable which is the value of $time, so that will give you the time that will be printed, t equal to that. Then x equal to, that's a label or that's a string, then you put the value which is in the b, and and here there is something also after this percentage. You can decide the format, whether you want to be printed as a decimal number, hexadecimal number, or a binary number. If you want it as a binary, x y g l e, I have specified it as a binary format. I want to print it, and single digit, so I don't specify. But for decimal, I have said 2 digit decimal number, because my times are like 0 0 20 40 60 and 80, so I don't need 3 digit. If I want 3 digit, I need to put 3 digit decimal number. Okay, so for example, if I change say here, if I say it is 50, okay, so I can do that, and it will overall time will go up to more than 100 nanosecond, so at least 3 digit is required, decimal number. So let us rerun this. Okay, so it is still not going. Okay, it's only up to 90 it has come. So let me just push it little more so that it will go to say 80. So now at least it should go. Maybe to be on the safe side I'll put 60 here also. Should definitely go to 3-digit. Yeah, so you can see that it is displayed in 3-digit, 100, 160 like that. So the 3 spaces are allotted here also. Earlier it only 2 spaces are allotted. So let me see what will happen now if I make it 2. Okay, it is still printing, but space is not allotted. Only 2 spaces are allotted if it is to be. Okay, so that's the only difference. So when you put 20, it is just in 2 spaces. There is no space in between. But if it was t equal to, there is no space. But you can keep the space other way also. You can put a space here also. If you want a space, you can put a space here also. Similarly, this is like a string, so you can put space wherever you want. So those are some minor things. Okay, so now you got the space even with 2 decimal spaces, but that spaces will come here also. You see, it is coming here also. So that's the difference. Is it clear now?
Yes, sir.
So the dollar time will take out the time here, 20, 100, 160, etc. It will take out the time, and then t equal to is a label, and including this colon I have put here. So those are like a string, but percentage 2d, that's a format that you specify. It should be in decimal or binary. Say if you put hexadecimal, some ABCD will also come. But we never want it to be that way. Whichever is better for our visualization, that is what we have to put it. See, it is now 0, 14, 64. 64 is basically 100 in decimal. This is now in hexadecimal because I put H here. So that's it. So I never put time in hex. It's not a very convenient thing. It will create only difficulty for us to. We are not used to that system, right? So this is better. Okay, so do you have the mind to sit for another program? Are you all with me? Are you doing it parallelly or not?
Yes, sir.
Okay, you are getting all this output?
Yes, sir.
Okay, very good. So certain things you need to just by heart, like every command block will be having a keyword module, then input output. Then one of the way in which you can specify the design I have shown you. Now the same thing I can do it in a different way. So without this assign command also I can do it. So here the assign command is basically implementing a Boolean expression we are specifying, but instead of that we can use the primitives from the Verilog library in order to create this operation. Okay, we can take an AND gate primitive say, so for example, this is an AND gate. So first, okay, so there's a different way. So let me just do it and then I will explain. So wire W1, then and sorry, before that not. See, not when I typed, it is showing a color change. So that's a primitive which is available inside. Now the syntax is like, you can give a label if you want, say N1 or gate 1. I'll put gate 1. This is my first gate. It's a label only, and its output will go to W1. Its output will go to W1, and then W1, and then its input is basically Y. Okay. Then I'll take the next gate, and the gate. Here I am giving the detail of the hardware structure. Earlier I was only giving a Boolean expression. So now my gate 2, what it will take? It will take X. Sorry, it will have an output. So let me say it is W2. So output is W2, and the inputs are X, comma W1. Okay, the output of the NOT gate, I am connecting it to the input of AND gate. Other input is X. So that way I have implemented this line. I have specified the hardware for that line, okay, which is more detailed description. Earlier I was not specifying what should be the hardware. Now I am detailedly specifying how should be the hardware. Then similarly I need a NOT. This is gate number 3. So the output will be W3. W3 is basically wire. You can just think about it as wire. W1, W2, W3, these are wires, and its input is basically now X. So X is the input to a NOT gate, and the output is connected to a wire which is named as W3. Then another AND gate I require, that is gate number 4. Gate number 4 is an AND gate. It will have an output which is, say, W4. So I need to introduce that here, W4, and then its input is basically W3, and the other input is Y. So these are two input AND gates. So output is should be, the order is output first and then input. Okay, first input, second input. So I have implemented this also successfully, I hope. And then the next one, I think there is an NOR gate available. Yes, NOR gate is available. So I need only one more gate. So gate 5, and gate 5 I have two outputs. One is W2, the other is W4. Okay, and my output is what? My output is basically what? It is equal to, right? So no, E. Okay, so I did not use L and G. So this is my what? This is my I've noted Y. Noted Y means this is my G. So I can replace G here, and similarly here is my L. Okay, I don't need a wire there. these are this can be directly connected to the output port. So what are the things I removed? W2 I don't need, W2 I don't need, and W4 also I don't need. If you want, I can replace W3 with W2. Okay. Even if you don't do that, it's okay. So W1 is basically the not of Y, and W2 is not of X, and then from not of Y and X we are getting G, and from not of X and Y we are getting L, and from GL we get E. So I have implemented this also. So this is called structural specification. Okay, so this is the best way, or you can say the more detailed version of specification, and here we are clearly specifying how the what gate should be used to implement my comparator, NOT gate and gate. I mean, this is not only, I can use only NOT gate and or I can implement it only with NAND gate or NOR gate, the universal gates. That's possible. I can implement it with multiplexer also. There are multiple ways in which I can implement a particular Boolean expression. You have studied that in digital electronics, but I am not specifying anything in the earlier specification. But here I am saying it should be implemented in a particular way. There should be a NOT gate, there should be an AND gate, it should be connected like this, all the details and everything else. So so another thing I want to tell you is that you can just put A here. The mapping can be done even without doing this dot thing, but you need to be careful here. So whatever we have put inside, I am just putting here. The order should be same, the order in which I have defined here. So A is going to X, okay, B is going to Y, G is going to small g, L is going to L. You have to, if you don't map it explicitly by saying both the module or the block variable and the register variable, then you need to keep the same order. Okay, but that simplifies things. If you maintain the same order, accordingly it will be mapped. But we are not specifying. But if you put it the other way, you can change the order. The order is not important. You can keep say dot x in bracket A. You can keep at the end also. It will. But if you are giving like this, order is important. Okay, so let's see whether this will run or not. Should run. Right, it's running without any problem. Okay. Maybe we will stop here if you don't have any other doubts. Right?
Sir?
Yeah.
Sir, while writing the data flow command in the first day, like when we wrote the data flow command when we were assigning values.
Yeah.
So there we have to define the gate properties as in when we are doing AND operation.
No. We are only giving the Boolean expression there.
Okay. Yeah,
but that Boolean expression would be implemented by the software, not necessarily according to this structure. Okay, it could be implemented by using just NAND gate alone. We are not particular about it. We just want the function to come the way we want. We are only specifying the functionality. We are not specifying the detailed structure of the circuit, or what gate should be used, how it should be connected. We are not specifying. We are saying Boolean expression. We are giving the Boolean expression and said this function should be implemented. Okay.
So isn't that easier with respect to the structural one?
For specification, description, that is easier, yes. But as I told you, this is only the first step, right? After this step comes synthesis, which I have not discussed about, where you generate the circuit by using the computer. So when you generate the circuit, if you give this way, you will get this way only. If you give the Boolean expressions, you may get an implementation which is maybe using multiplexer or some other things, and it may be like more costlier implementation. Costlier in the sense it may require more area on your chip. It may not be the simplest minimal implementation. Okay, so the way you describe it in the Verilog has a influence on the next step. And the next step, if you want it to be smooth, sometimes certain programs will not be able to be synthesized. Now when you synthesize, you don't keep the test bench. Okay, test bench is only for simulation. This part you will not keep. You will only keep the first part. Even the timing thing also you won't keep. You only keep this part to generate the circuit. So synthesis step is after this. Okay, but while synthesizing, if it has to become, if it has to be in a better way to synthesize, structural description is the best. Okay, because we are giving more details to the synthesis software, and synthesis software is very costly software. It is because it involves much more computation, not just compiling a program. It is generating the circuit from your program. So it has to read the program and understand what all hardware, what is the way to implement the hardware. So it depends upon the way the synthesis software is runs, it will generate the circuit. So sometimes, to make it easy, maybe it will be most of the cases I have seen, it will be implemented using some multiplexers. You have learned that, right? How to use multiplexer to implement a Boolean function. So because that has some advantage from the synthesis point of view. But if you want your hardware to look like this, then with this connection which I have shown, okay, this is not the only way to implement this Boolean function G, E and L. There are other ways to do that. Okay, I can instead of using NOR gate, I can use first a OR gate and followed by a NOT gate. That is another way we can implement it. But if you structurally specify it, it will be implemented with the NOR gate only, because we are specifying that. So there is a difference from the synthesis point of view, but for simulation, it's not any different. You are getting the same result, right? So right now we are only doing simulation. So we get the same thing here and here. And if it is only simulation, any of the way you can just you don't need even to do this much also. You can use if command. If a equal to b, then e equal to 1. If a is less than b, then l equal to 1. If a is greater than b, so that way also you can write. You don't need to specify the Boolean expression also. You just so that's another way of writing the code. So that's procedural programming. Okay, so basically structural programming and procedural programming, and then the assignment statement is something in between. Okay, clear? Any other questions? So you do it, and I'm going to give you a problem for you to do it yourself. So I will just give the hardware here. You have to implement, that is your experiment number 1. So basically you need to first construct a half order, and so part 1 is right, Verilog module for half order. Everybody understand what is a half order, right? Order, and then second part, structurally implement, or rather describe. I should not use implement, these are description. Describe a full order using half orders and Colgate. Okay, so first part you are free to do in any way, but second part I am insisting that you do it structurally. Okay, and thirdly, write a Testbench to write a Testbench and test your full order. That's it. Description. Okay, so I hope you know the details. I'll just draw the diagram. So you need to implement. So this is, say, label it as half order 1. This is half order 2, and into half order 1 you give A, B, and half order has 2 output. One output is basically giving you A XOR B, right? A XOR B. So that will give to the input of second order, second half order. The other input is say carry in. So this is A XOR B. A XOR B. And then here you have A B, and then so here you will get A XOR B XOR C. So this is basically your sum output, and here you will get one of the input is A XOR B, and that will be entered with the CA, or let's just call it as C for simplicity. A, B, C, these are the C. And then I have AB here. Go to the, so this is basically my carry. This is my full order. sum and carry output. ABC is the input. So and the half order I am not specifying, you should know at least that, but you can implement half order in any way, but then use that for the rest of the description in a structural manner. Okay, so this is basically your experiment number 1. So you take the program which I showed you, and then the easier way is to modify it and practice, and by modifying it and practicing it, you will learn it. Okay. You probably know what is this, right? This is generator, carry generator, and this is carry propagator. Okay.